Hello and welcome back to Emulating Risc-V in a high-level language. In today's session, we're going to extend our OS emulator. Previously, we added two system calls, which allowed us to write data and also to exit the program. And today's session, we will be adding the capability to open a file, read data out of it, and then close the file. In order to do this, we will need to extend the OS emulator, but make no changes to the actual Risc-V emulator itself. So focus will be on the OS emulator today. So let's jump straight into this. So if you recall, we have this OS emulator class, and the OS emulator class is where we dispatch the requests from the user program and perform actions on its behalf. So what we'll do then is we'll add three new system calls. Let's start with the first one, which will be the open system call. Let's give it the number 2. And we might as well write the other two system calls. Uh, Let me change my mind here. I'll call open 3 and then close will be 4. So there are 3 new system calls. So let's start by writing the read system call because it's going to be very similar to the write system call. So if you recall from write, let's take a look at what write does. So like any other system call, it needs to retrieve the values that the user put in registers that refer to the parameters to the system call. And just like with a write system call, the first parameter for the read system call is going to be passed in register 10. And we'll use the variable handle for this as well. The second parameter is going to be the address of a buffer, just like in the write system call. And the third one will be the length of the data in that buffer. And then we will create actually issue the emulation in a new method that we'll call read from handle. And then at the end of this, we want to update the emulator's register state. So we set the result register with the result value. So a quick review. Remember that the registers X10, X11, and X12 are used to convey the parameters into a function, and then X10 is used to extract the result of a function. So what we're doing here is we're extracting the parameters out of the register state, the emulated processor state, and then we're feeding it to this function that we're about to write. And then when that returns with a value, then we return that result into the register processor register state in register 10. So let's see what write to handle did, and we'll probably do something very similar in 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 the read case. So it's going to be a function that returns an integer, read from handle, and it takes a handle and an address and a length. So the first thing we need to do is make sure that the handle is valid. So if it's not, we'll return -1. And again, we are not putting a heavy emphasis on correct error handling here. We're not giving the programmer much help if something goes wrong, but again, this is not meant for production yet anyway. So that was that. Now we are going to call the actual operating system that I'm running on and ask it to read data. So first I need to create a span, and the way I do that is I say span and then memory get span at the address and the given length. And I'm trying to, I'm reading data from the file system and I'm writing into memory. So this is going to be an access mode write. I want to write to the chunk of data that I'm writing to. And then finally, after I'm done, I am going to pick the handle that I just validated it was correct. And then I'm going to say read into that span. Now, excuse me, the read function, when it successfully returns, will give me the number of bytes that were read. And then we return that as our result. However, should there be an error, then we return -1. So this system call is roughly based on the POSIX system call open, or sorry, read, but obviously the error reporting is much scaled down and not conformant. Great, so there's our read function. And there's nothing really much more to say about this. We read data and then we put stuff into the span and then we return the number of bytes read to the caller. So that wasn't that hard. Let's take a look instead at open, which is the more exciting system call. So open, what we want to do with open is, well, let's take a look at documentation for open, which I conveniently have opened over here. This is the Linux implementation of the POSIX standard. Open takes a path name and some flags. So what we'll do is we'll do something similar to this. We'll take a path name, which is the file name of the file that we want to open, and then some flags that will control what kind of open we'll be performing on the file. In some cases, you might want to open a file to read the contents. In other cases, you might want to open the file and truncate it and then write to that file. In other cases, you might want to open the file and leave it the way it is and then perform both reads and writes on it. So we will need to support a few modes, and those modes are specified in this flags parameter. So let's see. So we'll do the same job as before, where we go into our big switch statement here and implement syscall open. And here we don't have a handle, we have a path. So we'll say path is the first register, and then the flags is the second register, or second argument register, I should say. All right, and then we will create a new function called open file handle, and the result would be the resulting file handle, like this. And then finally, we will return the resulting file handle into the result register, which is x10. Good. Now we need to implement the open file handle. So what does that look like? So the first argument is going to be the path. Now the path is, this is actually an address into memory where there should be a UTF-8 encoded string. And we need to take that out of the memory and unpack it and return it as a string. So let's see, I've forgotten if we already do this in our project. And doesn't look like we are. no, this is the yeah, this is the opposite direction. Okay, so we're going to have to write some logic that extracts a string out of memory and gives it to us as a C-sharp string. So we have our memory, and we're going to ask it, what about we say get string? Let's get a zero terminated string. So the string that we're storing in memory will be a C string, which is terminated with a 0. And so what we'll do then is pass in the address of the string, which is path, and out comes a string. And of course, if anything fails, if we crash for whatever reason, then we return -1. All right, so now that I have my 0 terminated string, I need to take the flags that were passed in, and we need to translate those flags into something that the .NET Runtime can cope with, because what it will do is it will want to use the file stream abstraction for the handle. So what I'll do is I'll say file stream equals, and then new file stream. And what we'll do is we will pass in the string that we translated from the path, and then the some access mode. So we'll have to create a variable called access mode, and we'll start with it being initialized to 0. And then what we'll do is, depending on what flags are set, we will modify the access mode and pass it in here. Now that we have a stream, we're going to add it to the first available slot in our handles table. So we'll need to loop through our handles, and I'll check to see if any one of those handles is null. If the handle is null, then it's an available slot. And so what we can do then is set it to the stream that we just created. And we might as well return at this point with the slot number I. And let's declare this variable outside the for loop so that we can reuse it. So if we can find a null handle in our handle list, then we will deposit our newly created stream inside of that slot and then return the slot number. Otherwise, we will need to add a new handle. So what we'll do is we'll say handles.add, and then our new handle, our stream, and then we'll return the index, which, let's be strict about this. Let's say handles.count -1, like that. So that will return the index of the most recently added handle, which is this one right here, and that will return to the caller, which is up here, and the caller will put that in our register 10. So that looks good. Now, we need to implement get 0 terminated string, this utility method that we've added to the memory class, and we also need to unpack the flags and put them into the access mode. Let's start with this one, get 0 terminated string. So what should it look like? Well, this is not actually a path. This is actually an address to adder string, is what I'll call it. And I'll call it UTF-8 string, just to be clear that we're expecting a UTF-8 string. And I'll cast this to a uint so that we don't get these compiler errors. And now what we can do is then start looking for the memory address and keep reading bytes until we find a 0 byte. So what we'll want to do then is do this. We'll have this dot read byte at the address, and we'll start by initializing our address at that location, and then we will try to read the byte. This, so we'll say byte b equals this read byte, and if the byte is equal to 0, then we break this loop, and otherwise we increment the address and then we continue. So this loop will repeat until we read a byte of 0, or if we end up reading off into invalid memory. In that case, we'll throw an exception. At this point, though, the address variable that we have here is now pointing at the 0, and we have kept the original value adder UTF-8 string. That's the start of the string. So now what we need to do is just grab those bytes and extract them. So what we'll do is we'll say span equals get span, and starting at the address adder UTF-8 string, and here inconsistently we need an int, and then we want the length, which is going to be address minus adder UTF-8 string. Let's make a variable called length, which is equal to the int cast of this. Like that, and then we'll pass it in. And then what we're trying to do is read this data. And now we have a span, and then we can then ask the .NET runtime to give us a string. And that string is going to be encoding UTF-8 get string from the span. And we're done. Let's make that a public method. So now we have read the file name. Okay, so now we need access mode. So access mode will be built up from the flags. And if we go back to the POSIX or Linux documentation, there are a few kinds of access modes that we have to specify, which tell the operating system how we're going to be reading this file. Are we going to be reading from it, writing to it, or both? So we need to supply those flags. So let's add those to our constants here. And we'll give them public constant values. So let's give read only the value 1, write only the value 2, and then read write the combined value of 1 and 2, which is 3. So those are the access modes. But then we also need to specify how we intend reading the file. And so there's all manner of modes. There's append and async, but the ones that I'm going to be implementing are ocreate and where's the other one? Oh my goodness, so many. Maybe it is such that if you don't specify a creation flag, then that defaults to read. Okay, let's assume that that's the case. This we can always change this in the future, but we want to add this new flag. And did they call it create? They did call it create. Shall I continue the tradition? I will continue the tradition. I pick a flag value that is not going to conflict with any of these previous flag values. This flag will be used when we're creating a file. Of course, if you feel like it, you can always add more of these flags later. But what we want to do now then is unpack the flags here and translate them into the appropriate values for the read or the open API in .NET. So let's see. So we'll need a file access and a file mode. So by default, the access is going to be read. That's a healthy default, and the access mode by default is going to be file mode open. Open an existing file. Let's call this mode. Just the naming is confusing here. So we'll call this mode like that. Now, we need to look at those bits in the flag. So if flags and O underscore read only or write only, if that is equal to read only, then the access should be read. If the flag is write only, then the flag should be equal to access write. And if it's read and write both, then we have to specify read write in our access. And then we need to implement our mode. So the mode will be open by default, but if flags and O create is not equal to or is equal to O create, then the file mode is actually file mode mode equals file mode dot create. Good. The other file modes and accesses are left as an exercise to the watcher. Right, so now we can create files, we can open existing files. That's good enough for the purposes of our demonstrations. All right, so now that that is done, we're done with the open system call, and we can now proceed with the close system call, which is considerably simpler because all it does is it takes a single parameter, which is the handle we're asking it to close, and then we just close it. So we get the argument register and we call result equals close handle and then break after returning the result. So now we need to implement the close handle method. And the close handle method, what it will need to do then is take the handle value and find it um, in the list of handles. So if the handle is not valid, then we return -1. So if it's invalid, then we just return -1. But if it is valid, then what we'll do is we'll take the handle at that slot and close it. So we'll take the handles of handle and we close it. Of course, this might throw an exception, so we'll wrap that in a try-catch handler and return it -1 again. If that should fail. But otherwise, if that was successfully closed, then we need to clear out the handle slots. And make that a null. And then the slot has been cleared, and now we can return 0, which indicates no error. Okay, great. So now we have our system calls. So we need to test them. We need to make sure that this works as expected. So let's go to our main program and let's tear out the existing program, which is probably not doing anything interesting here. It's a leftover from previous work. We'll just clear that out there. So the program that I'm going to write now is going to read the contents of a file and display them on screen. It's not going to be very complicated. So what we'll need is somewhere a string that gives us the path of a file name. Let's create that file first of all. I'm going to go to my file system and I'm going to go to my Windows temporary directory. Here I'm going to create test.txt and it's going to be hello world because why not? So if I look at test.txt, we have hello world and this file is 14 bytes. Okay. So now we go back to our program here. So what we need to do then is, if I were to write this in a high level language or a medium level language like C, I would write something like this. I would say int handle equals open. I'd pass in the string, which is going to be c dot backslash temp backslash test.txt, and I'd pass in the flags O RD only. And then once I have that handle, I would need to have a buffer someplace. So let's assume that there were a buffer, or we could make a buffer in our program. So we would do something like car buffer of 1024, just like this on the stack. And then we would do read using the handle, put it into my buffer, size of buffer. That would read the number of bytes, and I would have the number of bytes read in CB. And then I would, of course, we want to check for errors here, but we're keeping the code simple. We're going to assume that everything is working properly. Then we would do a write to handle number 1, which is the standard output. So this would copy the contents of the file into the screen. And we want to write the number of bytes that we receive from reading. Now this will only read 1 kilobyte of data. So if the file is larger than that, it will stop. So if we want to make this program a little bit more interesting, we could change it into an endless loop like this, where we open the file outside the loop, and then we read a chunk of bytes. And if that is less than or equal to 0, then we break. There's nothing more to do. Either there's no more bytes to read or there was an error. But if it did succeed, then we do want to write. So this is the program that we would write in C to type the contents of the file C:/temp/text. But I don't have a C compiler, I have an assembler. So I have to translate this program into the corresponding assembly language statements that would do the same job. And it's trivial but tedious to do this. I'm going to reorganize the program a little bit. I'll put these big fat variables here. I also want to do an exit at the end of the program because it's polite. And then instead of this, I would call this my path. I call it a path. And then down here, I'd have a variable, and I would call it path, like that. Okay, so this is the program in C. Now let's translate this into Risc-V assembly language. So we need to invoke the open system call. In order to do so, we have to set up the 17 register, which, if you recall from the OS emulator, it's the register that is used to determine which system call we are going to be implement or emulating. So we need to set up register 17 to the system call number for open. So let's do that. So we'll use the load immediate method, and we'll take the destination register 17, and the immediate value is going to be, well, here we need the global address of the buffer. And if you remember, the way to obtain that is to do this AIUPC, AIUIPC, and then register 17, and then we need to get the high part of the symbol path. And then we need to add to that the low part of the previous instruction. And this is something that we went into at length when we talked about relocations. Getting the address of a variable in Risc-V requires, in general, at least two instructions. We have to add up these two halves of the pointer to get the final result. But I'm being dumb. This is the wrong variable. This is actually variable 10, which is the input parameter to the open system call, which is a string. So I apologize for that. I'm not thinking clearly. What I wanted to do was, and I was jumping ahead, what I wanted to do is just set the system call number. And the system call number is going to be osemulator.open, this one. There we go. So the system call selector has been initialized to syscall open. This is good. Now we have initialized the path to the number or the pointer to the string down here. And then finally, we want to add the RD only flag. So we'll put that in register 11. All right. So now we've done open. And for fun, we can do this. And we should add a comment here that at this point, well, first we need to invoke the system call. So we'll call the eCall. I think all these are zeros. We can ignore them. So that we have now called the system call, and we have handle in X10 register. Right. So now we have a for loop. So we'll have to implement a label for the for loop. This is going to be the loop top. And then we have another label, which is the loop exit. Done. And then inside the for loop, we will perform a read. So we will need to take the, oh, here we go. Immediate value 17 registers the selector of the system call, so we need to select system call read. And then we need to initialize the 3 registers for the read system call. And the first one is going to be the handle that came out of the call to open, but now we need to be careful. And this is one of the many of the the many low-level details that you as an assembler language programmer will have to deal with. After the call to read, the X10 register, which on input is providing the handle, on output it provides the number of bytes that were read. So if we don't save a copy of the handle in register 10, we will lose the handle, which is not good. So we need to copy um, the handle into a temporary register. And so let's put that in register 8 for no real reason. Um, we'll put the register 10 into register 8 using the add I instruction, which is, as you recall, takes the register value of the register 10, adds the literal number 0 to that, which is the same thing as the contents of register 10, and puts that into register 8. So register 8 will keep this handle value safe. In fact, let's move it outside of the loop because we don't need to copy it over and over again. So this happens outside the loop. All right, so now what we'll do is we'll take the value that we copied into register 10, or register 8, and copy it back into register 10. And this might seem like redundant the very first time we are going through the loop. Register 10 and register 8 will be the same, but after the read and write, they will not be the same. And so we need to hang on to the register 8 and then copy that back into register 10 right before we call a read or a write. So there's our register 10 all initialized and happy. Now we need to do the AIUPC trick again for register 11, the second argument, which is going to be the buffer. So we need to pass in the address of the buffer, which we haven't defined yet, but we will shortly. And then AIUPC is followed by an add I, where we pass in the same register and then the PCRel low -4. Again, the same pattern as in previous examples. And finally, the size of the buffer, which we'll make assumption here that it's going to be 10,024 bytes. So we will load immediate 12 with 1,024 bytes. And that number, by the way, is not too large. It will actually fit into the add immediate field, which, as you may remember, is 12 bits wide. 1024 is just, well, it's below that size, so we shall fit in 12 bits. All right, so now we've set up all the registers for the read system call, so now we can actually call it. And then at the end, number of bytes read in X10 register. So that's that system call. And then we need to check to see if the number of bytes that we read is 0 or equal to 0, 0 or less than 0. That's an error condition. So what do? We will use the branch less than, let's see, greater than or equal is what we want, but we need to switch the order. So I'm going to be doing the equivalent of this. So if 0 is larger than or equal to the number of bytes, then we break. And then we use BGE. Now notice I'm not using the unsigned version here. I'm using the signed version of the branch greater than or equal. because we need to treat the return value that's coming out of the system call as a signed number. And so it's important as an assembly language programmer to remember whether the comparison should be made as a signed or an unsigned number. In this case, this is a signed comparison because -1 is a negative number. And so we compare register 0 with the count of bytes which came out of register 10. And if that is greater than or equal to the register value 10, then that means that the value is 0 or less than 0. And then we go to loop exit. So that's what that does. And otherwise, we need to set up for another system call, which is the write that follows. So let's copy a lot of this. A lot of these are going to be similar. But instead of read, we now do a write. And we need to update the handle because the handle got stomped on, or the value in register 10 that came out of the system call for reading is no longer a handle. It's the count of bytes that were read. So now we need to restore that value, and instead here on the number of bytes that we want to write, we'll use the value in register 8 and put it inside of register 12 using the add I with a 0, which as usual is the way that we copy register values on Risc-V. We don't really care about the number of bytes that we wrote in this simple example, but we do want to go to the top of the loop once we're done, so we call that loop top. And that's the end of our loop. And then at the end of the loop, what we want to do is exit the program. So we say load immediate 17 with OS emulator, syscall exit. We probably should do a close though, just to be proper. We did implement the close system call. So let's do that. Let's close this correctly. And so we select the system call for closing, and then we have to copy the handle from register 8 back into register 10 again because it keeps getting clobbered. And then we issue the system call. This should close that handle. And finally, when we're done, we are now ready to terminate the program. And we want to give a status code in register 10. So we'll say register gets a status code of 0, which means everything went well. And then we issue the call to the operating system. And at that point, our program should terminate. Okay, now we need to create our buffer. So the buffer, let's see, how do we do this? We say define, we have a define word. And with a label, that's just one single number. That we need a mechanism to define a large number of bytes. So we'll do this. We will go to the definition of DW here. And what we'll do is we will create an overload where we say this is the word that we wish to write, and count is the number of times we wish to write it. Sound fair? So what we'll do then is we'll say for I equals 0, I is less than count, increment I, and then a little loop here which writes that value that many times. Let's use that now to define a buffer of zeros, and we need 1024 divided by 4 such zeros, remembering that a word is 4 bytes on the Risc-V. And then we need a label as well. The label for this is going to be buffer. That was that. And now, finally, we need a label for the path. And then that path is defined as a string, and it will take our string like so, and that should do it. That should be our program. And as you can see, writing in assembly language is a lot more tedious than writing in even a medium language or medium level language like C. It's very verbose. There's a lot of chattiness going on here because you have to explicitly specify which registers get which values at every turn of the program. There's a reason why higher level languages were invented. But this is our program, and naturally it will not run the first time, but we'll try it anyway. Let's try building it first of all, make sure that everything is compiling. And it looks like we are building correctly, so let's try running the program and see whether it successfully runs. I don't expect it to, but I would love to be surprised. Okay, so something went wrong. We are trying to access a page past... Ooh, interesting. Interesting. So this is because when we create our assembler, we give it a chunk of 1024 bytes initially, and that's not going to be enough for our little program, which now has a large buffer inside it. So let's make that bigger, and let's try that again. And this, of course, brings up some other issues. We shouldn't have had to do that manually. The assembler should have allocated the memory for us. But we'll get back to that in a future session. Okay, so now we're trying to write the bytes. These are the bytes that we're trying to write. Okay, now why is it so unhappy? Let's take a look at the context in which this is happening. Okay, define string. So this is happening inside the assembler. Now why is the assembler unhappy? We have a bunch of writes. This is our path that we're trying to write. We want to write it at this address. This should give us... Oh, there's a bug. We need to use the offset that came back. Okay, so this is the bytes to write. We need to write them at address offset. That's an interesting bug. I'm surprised we didn't run into this earlier. All right, let's try that. Let's fix that. Bytes to write, maybe? These are the bytes I want to write. I want to write them there at the offset. Yeah, okay. Not sure why. Okay. So we're getting an internal exception, not supported exception, in one of our system calls. It's probably the open system call. So let's put a breakpoint in the open system call and see why it's unhappy. here and run it. Okay, so here's our handle. Oh, we got past, it's actually a read. All right, so the handle should be a number. And the handle is handle 3, that looks good. And the number of bytes that we're reading is 1024, and that also looks good. And that did not throw an exception. So now the result should be 14, the 14 bytes of the file. This is good. All right, so let's put another breakpoint here and handle the next system call. So this next system call should be the right system call. So let's make sure that indeed is the case. It is the right system call. The handle is still 3. The length is now, oh, that's wrong. The length is wrong. The length should have been 14. So we made a mistake in our assembler. Let's go back to our assembler and fix that. So the number of bytes to write, okay. So, so here we have a problem. Um, yeah, it's an ordering issue. We, we, and I made a mistake again. So at this point, right here, register 10 contains the value of the number of bytes that we wrote. And the problem is that I need register 10 to contain the handle before I make my system call. So I copy over the handle over the value 10, but that clobbers the actual count of bytes. So that causes a problem. Um, Also, the system call that I want to write to, the actual, the, or sorry, the handle that I want to write to is not handle 8. That's the file we're reading from. What we want to do is write to the standard output. So there are a lot of bugs in here. I didn't faithfully implement what I wrote in the original C code. What I instead want to do is set load immediate into register 10, the first parameter of the system call. I want that to have the value 1, which is the standard output, the display or the terminal. And then here, instead of copying that file handle, I want to copy the value of register 10, which after this first read system call should have the number of bytes that I want to write. Now that should behave a little bit better. Let's try that. Let's skip over these breakpoints because now I have more confidence. And we got the first letter. So there, we got the first letter. So that's interesting. Why did we only get 1 byte? So let's go and take a look at our OS emulator. The write system call is something fishy going on here now. Let's get rid of this breakpoint and let's run this. So we know the read read 14 bytes. That's good. Now when we do a write, the handle should be 3. Oh, sorry, 1. Damn it. 1 is the standard output. That's correct. The length should be 114. And it's not. It's 1. So again, oh yeah, oh yeah, I know why. So here again, I've stomped the register 10 with the file handle 1, which is the output, standard output file. So let's move this statement up here. I mean, I'm reordering these. The reordering is fine, but it allows me to copy the value of register 10 that came out of the read into the register 12 where I need it for my write call. Before I stomp it, stomp the value in register 10 with a value 1, which is what I need for it to write the output to the display. Okay, feeling a little bit more confident now. Let's run this again. And there's our hello world achieved with a lot of pain. And the close seems to have worked, and yeah, this is our little program now. It's now able to open a file, read the contents of the file, write this to the display, close the file, and then close the program or terminate the program itself. All right, great. So we're almost at the point where our little OS simulator could start performing useful duties and become a useful piece of code. But there's one more thing that I want to add, and that I will be adding in the next session, and that's going to be command line arguments. One of the things that we want to be able to do is provide the name of the file. Unlike in our current program, the name of the file is hardwired in this variable here, path, but I would like to be able to specify that as, as part of the commands given to the command line. And so in the next session, we will do exactly that. We will add command line support for our OS simulator. And at that point, we can very generally read and write any files we want based on whatever arguments are passed on the command line. So until that time, I wish you all well and hope to see you back then.